In continuation of the last videos on aromatic halogen compounds of BSc Part 1 Organic Chemistry, in this video we will study nucleophilic substitution mechanism. In aromatic halides, nucleophilic substitution reaction can be held through following two mechanism: bimolecular addition elimination mechanism, or second, elimination addition or Benzene mechanism. Aromatic halides do not show SN reaction through unimolecular SN1 mechanism, since halogen atom is tightly bonded to carbon atom of benzene ring. So first let's take bimolecular mechanism. From chemical kinetics, it's observed that the rate of the reaction is rate is equal to concentration of halobenzene into concentration of the nucleophile. That is, rate of the reaction depends upon concentration of both halobenzene and nucleophile. If electron withdrawing group is attached to meta position with respect to the chloro or the halo group, then the rate of the SN reaction is unaffected. But if the electron attracting group is present on the ortho and para position with respect to the chloro or halo group in the benzene ring, then they give nucleophilic substitution more easily. So for example, let's take reaction of para-nitrochlorobenzene with aqueous NaOH at 400 Kelvin. So here we see that nucleophile attacks that carbon atom which is bonded to halogen atom, forming an anion. The carbon atom with which halogen was attached now is bonded with the nucleophile also, and the carbon C1 in this case attains sp3 hybridization state from the sp2 hybridization state, and the electron pair of the double bond between C1 and C2 shifts on the second carbon atom, and this attains negatively charged, and we see that the aromaticity of the benzene ring is affected. Then by resonance effect we get three structures in which the negative charge moves from the second position to the oxygen of the nitro group, and from the oxygen of the nitro group to the sixth position of the carbon atom of the benzene. In this way, the anion formed by the attack of the nucleophile is stabilized. In the second step, removal of the halogen atom as halide from the carbon ion re-establishes the aromaticity. So here we see that the bond between the carbon and the chlorine group shifts on the chloro, and the chlorine is eliminated as chloride, and this negative charge, which is at the sixth position atom of the benzene ring, shifts between C1 and C6 and forms a double bond there, and the aromaticity is re-establishes. Next we come to the Benzene mechanism. Aryl halides which do not contain electron attracting group at ortho and para position do not give nucleophilic substitution reaction easily, but in a drastic conditions they show nucleophilic substitution reaction. For example, chlorobenzene reacts with NaOH at 613 Kelvin and high pressure to give phenol. Bromobenzene reacts with amide in the presence of liquid ammonia to give aniline. Such reactions are explained by the Benzene mechanism. So if we see the Benzene mechanism, it takes place in two steps. In the first step, amide ion, that is nucleophile, abstract the proton which is eliminated from the ortho position of the bromobenzene group, and the negative charges develop at the ortho position to the halo group, for example bromo group in this case. And in the next step, the bond between the carbon and the bromine shifts on the bromine, and the bromine atom is eliminated as bromide, and this negative charge electron pair shifts between the carbon which previously was bonded with the bromine and forms a double bond. So now C1 and C2 has triple bond, and this is a benzene structure. So we see that bromobenzene, first by the elimination of hydrogen ortho position hydrogen as proton, and then simultaneous elimination of the bromine as bromide, forms benzene. In the second step, the benzene adds nucleophile and forms a substituted product. So what happens first, that one double bond electron pair shifts on the carbon atom and anion is formed, and this amide with its electron pair bonds with the carbon atom. So this aniline anion is formed, in which the negative charge is at the ortho position to the NH2 group. In the next, the bond between hydrogen and nitrogen of the ammonia breaks and shifts on the nitrogen forming amide, and this hydrogen, which is eliminated as proton, attacks the negative charge carbon and aniline is formed. Now we come to the characteristics of reaction benzene. The incoming nucleophile can either bond with the same carbon atom, that is attached to the same carbon atom from which halogen atom has been eliminated, or it can bond with the carbon which is ortho to the leaving group. For example, if we take the example of labile carbon, the two types of 1 and 2 of aniline are formed. So chlorobenzene, in which the start carbon is the carbon with which the chloro group is attached, it undergoes reaction with amide in the presence of liquid ammonia. Then we get two types of aniline. First, in which the NH2 group is attached to the labile carbon, that is the carbon to which the chloro group was previously bonded. And the second is that NH2 is attached to the ortho carbon. Aniline group, this NH2 group is attached to the carbon which is at ortho position to the starred carbon with which the chloro group was previously attached. So we get two types of products. In the first, the incoming group is attached to that same carbon with which the leaving group was attached, and in the second, the incoming group is attached to that carbon which is ortho to the carbon with which the leaving group was attached. So the two types of anilines are formed when amide ion reacts with arene. Halide having isotopic carbon with the label isotopic, as we have seen in this case. If both the ortho positions, that is 2 and 6, with respect to the substituent are already occupied by other groups, then the acid reaction does not take place via Benzene mechanism. So if we say take 2-chloro 1,6-dimethylbenzene and make it to react with amide in the presence of liquid ammonia, then we see that no reaction takes place. Then third, we see the formation of all the toluenes can be explained on the basis of the formation of the benzene as an intermediate. So here we see that this is chlorotoluene and it is metachlorotoluene, and the chlorine is at the meta position with respect to CH3 group. When it reacts with amide, then we see that two types of benzene are formed. In one type of benzene, the triple bond is between C2 and C3, and in the second, the triple bond is between C3 and C4. So the benzene with triple ion between C2 and C3 on reaction with ammonia gives rise to ortho product and meta product, while the benzene having the triple bond between carbon 3 and carbon 4 gives rise to meta product and para product. So these four types of products are obtained only because the reaction is through benzene mechanism. Next we come to hydrolysis of parachlorotoluene at 350 degrees centigrade forms a mixture of two isomers of glycerol. So we see that this is parachlorotoluene reacts with HOH, that is it undergoes hydrolysis at 350 degrees centigrade. Then we see that paracrysol is formed and metacrysol is formed. This is again due to the formation of the two types of benzene, whether the triple bond is between 2 and 3 or whether the triple bond is between 3 and 4. Next we see that the bromomacetylene does not have any hydrogen atom on the carbon atom adjacent to the carbon atom bearing bromine. So here both the ortho position to the bromine atom are occupied, and if this compound, that is bromomacetylene, undergoes reaction with amide in liquid ammonia, then we see no reaction takes place, as we have considered before also. When ortho fluoromethyl chlorobenzene is treated with sodamide, that is NaNH2 in liquid ammonia, only meta trifluoromethyl aniline is formed. And this can be explained on the basis of the stability of the anion formed during ortho attack or the para attack. This is ortho trifluoromethyl chlorobenzene, and when it reacts with amide in the presence of liquid ammonia, then we see that the benzene is formed, which is in which the triple bond is between C2 and C3. Now when ortho attack is formed, then anion is formed in which the negative charge is at third position, and when meta attack is formed, that is meta attack happens, then the anion is formed in which the negative charge is at second position. And it is seen that this anion which has negative charge at meta position is less stable, and this anion which has negative charge at second position is more stable. Hence the meta product is formed and the ortho product is not formed. Now we come to the structure of benzene. The structure of benzene has an additional carbon-carbon double bond in the benzene molecule. The additional bond is present in between the carbon atom bonded previously to the halogen atom and the carbon at ortho position to the halogen atom bearing carbon. The new bond is formed sideways, overlapping of the sp2 orbitals. This new bond lies on the side of the ring and has little interaction with pi cloud lying above and below the ring. The sideways overlap is not quite good and proper, and hence the bond is weak, making the benzene a highly reactive species. And the sideways overlap of sp orbital forms pi bond out of plane of aromatic pi bond, which makes the benzene species very reactive. That's all for today. Thank you.